Is the discussion of discussion set 3 position versus time graphs. Please check your own work while I go through the problems in the video. In our first problem, we've got a roller skater observed at the following positions and times. I have scaled the time axis 0 through 10 and scaled the x-axis 0 through 10, and the y-axis I have scaled at every line represents 5. So I would have 10 here, then 20 and 30. I've also titled the graph. Titles are important so that they draw your attention to what it is that's being graphed. So let's plot the points. We have 0, we're at 10, right here. At 1 second, which is halfway between the 0 and the 2, we are at 12. Maybe somewhere through, that would be 15, so somewhere up here. At 2, we're at 14, just underneath the 15. At 5, which would be out here, we are at 20. And 8, we're at 26. And at 10, we're at 30. You can draw a best fit line in. So something like this. Now, obviously we have some estimation occurring, so it's not a big deal if all the points are directly on the graph. Okay. So we've plotted our position versus time graph. Now I want to explain how you can use the graph to determine how far he was from the origin at 6 seconds. Okay, so at 6 seconds, there's a couple of ways that we could do this. We could write an equation for the graph, or for the plot, for the best fit line, or we could just describe it. So at 6 seconds, you could say that you could write this. Okay, so one can go along the x-axis. Until they get to 6 seconds. Then go up to reach line. Then trace to y-axis to read position. So in other words, you're just interpreting the graph, you're reading the graph. And that would be, if we go up to 6 seconds, we go across to 6 seconds, we go up the line, then we come over, maybe 22. So we can say we're approximately equal to 22 meters at 6 seconds. But that is an estimate. We then want to write a mathematical description of the skater's motion. So it is a linear expression, so that means we're going to need a slope. If you go back and look at the graph, our points are pretty well on the line. I'm going to use my 2 endpoints and say that the slope, which is actually the velocity, is going to be equal to 30 meters minus 10 meters divided by 10 seconds minus 0 seconds. That's going to give 20 meters divided by 10 seconds, which is equal to 2.0 meters per second. We also know, here's our slope, or m. We can also look at the graph and get b is equal to 10, which is the starting point. So we have the equation y equals, in y equals mx plus b form, that we have our final position, xf, is equal to 2 meters per second times a time interval plus 10 meters. That would be a very specific equation for this line because we have 2 meters per second and 10 meters. So we would say that this is the specific equation. And what it's specific to is it's specific to the motion of Robin, the roller skater. The more general form of this would be xf equals b delta t plus xi. And this is the general relationship, the general linear equation between position and time with constant velocity. So this is CV only. Okay. Next question is, was his speed constant over the entire interval? And the answer appears to be yes. How do you know? The pattern of position change through time is linear. Linear x versus t graphs show constant velocity. Of course, that constant velocity is the slope of that line. And number 2, in a second trial, the timer started her watch a bit sooner. The following data were obtained, and they want us again to plot a position versus time graph. I've used the same scale and plotted to get this linear plot. Okay, so there we are. Pause if you need to compare yours to this. How far from the origin was the skater at 5 seconds, and how do you know? Okay, the origin requires a little bit of discussion. So where is the origin? Generally speaking, the origin is going to be considered to be 0, 0, not the starting point. So what we would do is we would go across to 5 seconds, and we would come up and read the graph. So we're somewhere through here. I'm going to say 19. So approximately 19. Or x is approximately 19 meters. One more time on that. Let me fix this. Position is approximately 19 meters at 5 seconds. How do you know? And it's really the same as before. We're going to move across the x-axis until we get to 5. We're going to come up until we intersect the line, and then we're going to go across and read. So I'm at 5, go up until I intersect the line, come across and read. And I am, of course, over here, I'm estimating. I'm estimating 19. You could have easily said 18. Was the skater's speed constant? If so, what was it? Yes. And We can take the endpoints again because they're relatively close to the line and say that the speed, which is also represented by v, or you could use s would be fine. Speed is going to be the slope again. This would be 34 meters minus 4 meters divided by 10 seconds minus 0 seconds, and that's going to equal 34 minus 4 is 30 meters divided by 10 seconds. It's going to be 3 meters per second. Okay. Now, we're only looking for speed, so we don't necessarily have to write an entire equation for this. We can just use the speed equation, distance divided by time, and we're finding the distance. And since we have one direction of motion, our distance is really going to be here, the same as our displacement. So in the first trial, the skater was further along at 2 seconds than he was in the second trial. Does this mean that he's going faster? And explain your answer. Well, your starting point does not determine speed or velocity. So let's say speed / velocity. The first skater was further along because he started at 10 meters rather than at 4 meters. We've calculated the speed. The second skater was moving faster.